How many stirs do you see? The beaker and the water act like mirrors and lenses to confuse us. The experiments with water and colored oil are a simple way to show some aspects of a method to collect 1 million gallons of petroleum spilled anywhere in the oceans. One pulls water out from under an oil pool to make a depression in the surface and to make a current to push the oil together. Last time the message was in the words with video as background. This time we will try to explain the videos and their meanings. See a stir and a depression, a dimple in the surface. Colored oil will depress water more than air, both in the beaker cusp and in the Gulf oil pool. If we knew a relationship between water depression and oil pool depth, we might do useful experiments with water alone in Lake Ontario or the Gulf. First, these droplets will have to coalesce to form a cusp. The motion of the droplets gives us, more or less, the motion of the water. The needed surface current is formed to push the oil together. Spiral motion of the water down to the impeller is implied by the oil droplets near the cusp. Down motion causes friction at the oil-water interface. The other flows on the bottom and up the walls is not shown. Okay, but a cusp is of the wrong shape to hold 1 million gallons of oil. It is of small radius, its surface area and its volume are tiny. We want depth near the edge of the pool or over the entire pool. We start again with fresh water and the stirrer going. Where is the dimple? A shimmer indicates motion and turbulence, but what depth? We pour oil in, but there is a delay in forming the cusp. The cusp is not even over the stirrer. Those studying mixing found a power relationship for the depression of both oil and water, which fitted a pair of semi-logarithmic lines. At low power, the fit failed, and the oil-water interface is depressed more. That's what we've seen here. Good. For 1 million gallon of oil pool, power cost will matter. What would happen if we reversed the flows using, for example, a propeller or air bubbles instead of a magnet, to move water up instead of down in the center, and to flow down on the walls? Where would the oil go? Let us try to visualize something more complicated to get a better picture of our intention. Consider two beakers with the small one suspended inside the large one, under water and oil. A magnetic stir on the bottom of the big one throws water out along the bottom. The water still goes up the wall of the big one, but where will the water come back down, and where will the oil collect? Think about it when we do our hand waving. You will see a stationary stirrer at the bottom center, which will start up, but surface motion will be delayed. In the previous stop, water and residual centrifugal force pushed oil away from the walls. These excerpts are from a 14-minute run, which was filmed from both top and side. We'll see this start up again from the side to get a clear view of the cusp forming. In this top view, it is difficult to see the cusp, but first delay and then movement of the surface oil blobs are apparent. The delay is to allow momentum to accumulate. The blobs are pulled in enough to fill the cusp, but then they seem to displace each other and the outer ones fall behind the inner ones. In other runs, where more and more and more oil was added, the blobs formed a pool which grew thicker, but the cusp seemed unchanged. The switch to the side will be after adding green oil, whose dye is water-soluble. After a delay, the green will color the water at the oil-water interface and indicate its path. The beaker experiments show the advantage of beaker walls and bottom, and of the accumulation of momentum. The hand waving will explain how to enlarge and flatten the oil pool, and provide walls, and the density gradient may provide a bottom. The next episode will go into the technical aspects. Ocean waves slowly accumulate or lose energy, while the wind blows or ceases to blow, both over long times and distances. Google Wave and BEAUFORT, or LUD. Admiral Beaufort's observations were for the war with Napoleon. Ludd's tables help surfers search for the big waves using weather charts. If any of you are surfers and have a short video of a big wave breaking or being ridden, I would like to use it in my next Black Gold or Black Death number 3. We will not wait for the green to begin crossing the oil-water interface, but we'll skip to a run called Fast Green, which is fast. There is a better way to see fluid movement. Mark it with a grid of blue lines, instantly and without disturbance, and follow the movement in detail. I invented it at a lecture in 1960, reporting another failure in a 60-year attempt to explain friction, heat, and mass transfer in turbulent flow. Our results, using a pulse of UV light to turn a photochromic indicator blue and measure the statistics of the viscous sublayer, was published in 1967 and has been well cited since. I am adding the green oil. The green is just now beginning to come out. There's a thicker blob of it on the tip, coming down toward the stirrer. We've enlarged it so we can see more clearly. You can still see the stirrer. And if we wait a moment, there's some, well, it must be thrown out the outside. It's getting greener. And then we see sort of a wave of green coming up. I would like to try to relate what we've seen in the beaker to what we would be doing with 1,000,000 gallons of oil. Obviously the cusp is tiny and we need a big, large pool. It is of interest to us is the impeller throwing the water out the bottom, up the walls, and then converging to the center and the surface. The reason the converging is important is because that increases the velocity of the water. If the water's velocity is high enough, it will push the oil ahead of it. What happens is that you'll form a cusp of a certain diameter, depending on the flow rate, and the cusp will help the flow down, so the flow is much more efficient. Now what I want to do is to expand this from the beaker to the real world, to the Gulf of Mexico. I want to take my arms out, maybe 30 meters, maybe 100 meters, and have a small circulation, well, not that small, we're talking meters now, that's going exactly like we had before. In at the surface, out at the bottom. So that what we're doing is we're compressing a pool of oil together. I want to use my arm and hand as the impeller and cable. My arm is the cable, we don't need to worry much about that, but the hand is going to throw the water. This is a right-handed throw, and the palm moves smoothly through the water, and then when it hits the fingers it gets thrown to the side. A small amount, which means it will be following, or a considerable amount, in which case it will be leading, and I can of course cup the fingers so that I get acceleration. It's more of a jet.